Hello everyone, welcome to today's lecture. So we talked about the dynamic set last week. Many applications require a dynamic set that supports only a dictionary operation like insert, search, and delete. For example, a compiler that translates a programming languages maintains a system symbol table in which the keys of elements are arbitrary character strings corresponding to identifiers in the language. A hash table is an efficient data structure for implementing dictionaries. Although searching for an element in a hash table can take as long as searching for an element in a linked list, theta n, in the worst case. In practice, hashing performs extremely well. Under reasonable assumptions, the average time to search for an element in a hash table is actually theta 1. So even though the worst case is theta n, average case is only theta 1. A hash table generalizes the simpler notion of an ordinary array. Directly addressing into an ordinary array makes effective use of our ability to examine an arbitrary position in an array in big O1 time. We can take advantage of direct addressing when we can afford to allocate an array that has one position for every possible key. When the number of keys actually stored in is small relative to the total number of possible keys, hash tables become an effective alternative to directly addressing an array, since a hash table typically uses an array of size proportional to the number of keys actually stored. Instead of using the key as an array index directly, the array index is computed from the key. And we will see several aspects later. Direct addressing is a simple technique that works well when the universe U of keys is reasonably small. Suppose that an application needs a dynamic set in which an element has a key drawn from the universe U equals 0, 1 to m minus 1, where m is not too large. We shall assume that no two elements have the same key. However, the downside of the direct addressing is obvious. If the universe U is large, storing a table T of size U may be impractical or even impossible, given the memory available on a typical computer. Furthermore, the set K of keys actually stored may be so small relative to U that most of the space allocated for the T would be wasted. So to represent a dynamic set, we can use an array or direct address table T 0 to n minus 1 in which each position or slot corresponds to a key in the universe of U. So it's supposed like this, with the m is equals to 10, so the values key values can be represented as 0 to 9, and the actual keys may be 2, 3, 5, or 8. So then you can use those 4 actual tables to link to the satellite data. as this one. So basically, the actual keys maybe 2, 3, maybe 2, 3. So only these 4 out of the 10 is used, and then this will mark to linked to the actual satellite data. So it's because it's a direct address search. Basically, if you want to search the key K, basically you just return TK, like this one, TK. And if you want to insert the item, you just first check the item is empty or not, and then you can just insert it. Or if we assume that it's not it's always identical, then basically we can just simply change the T key K key X into X. So basically, if you want to add 7, then basically you just put the satellite data here, 7, and this is you have a new key here. So basically, and if you want to delete, you just clear the item. So if you want to delete number 2, you just put it into nil, then that's it. So basically, a direct address search is very simple, but the downside is also obvious. If the universe U is large, storing a table T of size U may be impractical or even impossible, given the memory available or a typical computer. Furthermore, if the set of K of keys actually stored may be too small relative to U, then most of the space allocated for T will be wasted. So the difficulty with direct addressing is obvious. If the universe U is large, storing a table T of size U may be impractical or even impossible. Furthermore, the set K of keys actually stored may be so small relative to U. Specifically, the storage requirements can be reduced to big O K, even though searching for an element in the hash table still requires only big O one time. So when the set K of keys stored in a dictionary is much smaller than the universe U of all possible keys, a hash table requires much less storage than a direct address table. Specifically, as we just mentioned, we can reduce the storage requirement to theta k while maintaining the benefit of searching for an element in the hash table still requires only big O one time. The catch is that the bound is for the average case time, whereas for direct addressing is holds for the worst case. So for hash table, the big O1 is only for average case, but for direct addressing, the big O1 is for the worst case. With direct addressing, an element with key K is stored in slot K, and with hashing, this element is stored in a slot HK. So in a hash table, we will use the hash function H to select a table for it. That is, we use the hash function H to compute the slot from the key K. Here, H maps the universe H, U of keys, into the slots of hash table T and 0 to n minus 1. So basically, we can say that the hash function H is actually mapped to the universe into the subset of 0 to n minus 1, where the size m of the hash table is typically much less than the u. We say that an element with the key k hashes to slot hk. We also say that hk is the hash value of the key. So basically, the hk will be the hash value. And this slide illustrates the basic idea. The hash function reduces the range of array indices and hence the size of the array. Instead of the size of u, the array can be size m. So basically, K1 will be stored in hash K1, HK1, K2 will be stored in hash K2, and K3 will be stored in hash K3, and K4 will be hash K4, and K5 will be hash K5. And there is one hitch. Two keys like this one may hash to the same slot. We call this situation a collision. Fortunately, we have effective techniques for resolving the conflict created by collisions. So as we previously stated, the hash function is a mapping from the universe to the key values 0 to n minus 1. So the hash table itself is basically an array of m elements with key from 0 to n minus 1. So when you want to map a value, an item with key value k, basically you will use its hash function to map to the hash table. And there may be collisions when two keys have the same hash value to the same slot. So basically, it's a problem that we need to solve when there is a collision. So the ideal solution would be to avoid collisions altogether. We might try to achieve this goal by choosing a suitable hash function h. One idea is to make h appear to be random, thus avoiding collision or at least minimizing their number. The very term to hash, evoking images of random mixing and chopping, captures the spirit of this approach. Of course, a hash function h must be deterministic in that a given input k should always produce the same output hk. Because the size of u is much greater than m, there must be at least two keys that have the same hash value. Avoiding collision altogether is therefore impossible. Thus, while a well-designed random-looking hash function can minimize the number of collisions, we still need a method for resolving the collisions that do occur. So there are two ways to solve the collision. The first one is called the chaining, and then we will talk about it in the following slides. And the second technique is called open addressing, which will be talked about later in the talk. So how can we solve the collision by using the technique chaining? In chaining, we put all the elements that hash to the same slot into a linked list, just as this figure shows here. So each slot will contain the head of the list of all the stored elements that hash to it. So if there are no such element, it simply contains nil, as is shown here. Basically, it's nil here. And otherwise, it will contain a linked list of all the elements. So for this example, K1 and K4 points to the HK1 and HK4 are all 1, so basically they all link it to the same slot here, so K1 here and then K4 here. And then also K5, K7, and K2 will be the same, all linked to the same link list, so it linked here, K5, K2, and 7. And then the 3 dictionary operations of a hash table T are easy to implement when the collisions are resolved by using chaining. So the first one, chained hash insert Tx. Basically, you just insert X at the head of the list Th key X, just as you show here. So if a new key is inserted into this hash table, basically if it's just if it's the same as K3, then basically you will be insert here. So by adding a new element here and then a new element to the K3 here. And then the second one, search, chain hash search TK. If we want to search a key K from the hash table T, then search for an element with a key K that has a hash table key K. So basically, you just need to search for the hash. So if it's K, if it points to somewhere here, then basically it's nil, so you know it's not inside the hash table. Otherwise, if it points to the here, then basically you just need to search through the list. So if the key equals K6 and then you just traverse through the list and then found, okay, yes, key 6 is what we want. Or otherwise, if it's not, then basically if after you search for the entire list, then basically you found out that, okay, it's nil, then it's not inside the hash table. And then the last dictionary operation is delete. So the chained hash delete with hash table T and item X, you just delete X from the list of the hash table with T H key X. So if it's in the list, in the hash table, basically you just delete it from the linked list. So the complexity of these three the complexity of these three operations. The worst-case running time for insertion is big O1. The insertion procedure is fast in part because it assumes that the element X being inserted is not already present in the table. If necessary, we can check this assumption at additional cost by searching for an element whose key is X dot key before we insert. For searching, the worst-case running time is proportional to the length of the list. We shall analyze this operation more closely later. We can delete an element in big O one time if the lists are double-linked. If the hash table supports deletion, then its linked list should be doubly linked so that we can delete an item quickly. If the list were only singly linked, then to delete element X, we would first have to find X in the list, so that we could update the next attribute of X predecessor. With singly linked list, both deletion and searching will have the same asymptotic running time. So now let's analyze the complexity of hashing with chaining. So how well does hashing with chaining perform? In particular, how long does it take to search for an element with a given key? Given a hash table T with m slots that stores n elements, we define that load factor alpha for T as n over m. That is the average number of elements stored in a chain. Our analysis will be in terms of alpha, which can be less than or equal to or greater than 1. So the worst case behavior of hashing with chaining is very terrible. It happens when all n keys hashed to the same slot, creating a list of length n. The worst case time for searching is thus theta n plus the time to compute the hash function. It's no better than if we used one linked list for all the elements. Clearly, we do not use hash table for their worst case performance. The average case performance of hashing depends on how well the hash function H distributes the set of keys to be stored among the m slots on the average. For now, we shall assume that all given elements is equally likely to hash into any of the m slots, independently of where any other elements has hashed to. We call this assumption of simple uniform hash. So it's a uniform distribution hashing function, and we assume it will take big O1 time. So for j equals 0 to n minus 1, let us denote the length of the list Tj by Nj. So the total number of nodes will be n equals n0 plus n1 plus blah 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 plus n minus 1. And as we can see, the average value of NGL is actually alpha, which is n over m. So the expectation value of each NGL will be equals to alpha n over m. And by the way, we change the value here. It's in the lower cases. So now we assume that the big O one time suffices to compute the hash value Hk, so that the time required to search for an element with key k depends linearly on the length of the list Thk. Setting aside the big O1 time required to compute the hash function and to access the slot Hk, let us consider the expected number of elements examined by the search algorithm. That is, the number of elements in the list Thk that the algorithm checks to see whether any have the key equal to k. We shall consider two cases. In the first, the search is unsuccessful. No element in the table has key k. In the second, the search successfully finds an element with k. So now we first see the theorem 11.1. It says that if a hash table in which collisions are resolved by chaining, an unsuccessful search takes expected time theta 1 plus alpha under the assumption of simple uniform hashing. Since we are talking about the average case, under the assumption of simple uniform hashing, any key k not already stored in the table is equally likely to hash to any of the m slots. The expected time to search unsuccessfully for a key k is the expected time to search to the end of the list T Hk, which has the expected length of alpha equals to n over m. Thus, the expected number of elements examined in an unsuccessful search is alpha, and the total time required, including the time for computing Hk, is big O 1 plus alpha. The situation for a successful search is slightly different, since each list is not equally likely to be searched. Instead, the probability that a list is searched is proportional to the number of elements it contains. Nonetheless, the expected search time still runs out to be theta 1 plus alpha. So here's the statement of theorem 11.2. In a hash table in which collisions are resolved by chaining, a successful search takes time theta 1 plus alpha on average, under the assumption of simple uniform hashing. So to prove that, we assume that the element being searched for is equally likely to be any of the n elements stored in the table. The number of elements examined during a successful search for an element x is one more than the number of elements that appear before x in the x list. Because new elements are placed at the front of the list, elements before x is the list were all inserted after x was inserted. To find the expected number of elements exempt, we take the advantage over the n elements x in the table of 1 plus the expected number of elements added to X list after X was added to the list. So let Xi denote the ith element inserted into the table for I equals 1 to n, and let Ki becomes the key. For keys Ki and Kj, we define the indicator random variable Xij that Hki equals Hakj. Under the assumption of simple uniform hashing, we have the probability of Hki and equals Kj in equals 1 over m. So the expected number of elements exempt in a successful search is something like this. So the expectation so the average, this is the average case, so it's 1 over n. So we have n elements because we are counting the average. So we sum up all the 1 elements, and then it's 1 plus the I equals 1 to n with Xij, they are in the same. So if they are the elements added later have the same list. You use the same list. So basically, this is the expectation, and so basically, as you can see from here to here, basically it's 1 plus alpha over 2 plus, minus alpha over 2n. So basically, a successful search would be 1 plus alpha because it's theta 1 plus alpha. So the reduction itself, just please go over yourself later. But what does this analysis mean? If the number of hash table stars is at least proportional to the number of elements in the table, we have n equals big O m, and consequently, if alpha equals n over m, then we have big O1. The searching task takes constant time on average. Since insertion takes big O1 worst case time and deletion takes big O1 worst case time when the lists are doubly linked, we can support all dictionary operation in big O1 time on average. So far, we talk about the characteristics for the hash table, which can perform the search operation in theta 1 plus alpha, and the insert and deletion in theta 1 time. But we left one important thing here. We assume that for all the hash tables, we assume that we have a good hash function, so that the hash function can uniformly distribute all the key uniformly. So all the key can be distributed in all the location uniformly. So what's left us is how can we find such hash functions? So before we tell you how to find the good hash functions, we need to first define what's a good function, a good hash function. A good hash function satisfies an assumption of simple uniform hashing. Each key is equally likely to hash to any of the M slots, independently of where any other key has hashed to. Unfortunately, we typically have no way to check this condition, since we rarely know the probability distribution from which the keys are drawn. Moreover, the keys might not be drawn independently. Occasionally, we do know that the distribution. For example, if we know that the keys are random real number k independently and uniformly distributed in the range 0 to 1, then the hash function hk can be set after kn flow satisfy the condition of simple uniform hashing. So if k is between 0 and 1, then hk may be defined as kn so that it can be uniform. It's a simple uniform hashing. So again, what's a good hash function? Basically, a good hash function is a simple uniform hashing that so for any key k such that hk equals to j, the probability is 1 over n. It's uniformly distributed by all the possible hash values. So, and we already say that yes, assume 0, k is between 0 and 1. The flow of k times m is a good hash function. So in practice, we can often employ heuristic techniques to create a hash function that performs well. Qualitative information about the distribution of keys may be useful in this design process. For example, consider a compiler symbol table in which the keys are character strings representing identifiers in a program. Closely related symbols such as PT and PTS often occur in the same program. A good hash function would minimize the chance that such variants hash to the same slot. A good approach derives the hash value in a way that we expect to be independent of any pattern that might exist in the data. For example, the division method computes the hash value as the remainder when the key is divided by a specified prime number. This method frequently gives good results. Assume that we choose a prime number that is unrelated to any patterns in the distribution of the keys. And we know that some applications of hash functions might require stronger properties than are provided by simple uniform hashing. For example, we might want keys that are close in some sense to yield hash values that are far apart. So we will also talk about universal hashing often provides a desired property. So most hash functions assume that the universe of keys is a set of natural numbers n equals 0, 1, 2, and so on. Thus, if the keys are not natural numbers, we need to find a way to interpret them as natural numbers. For example, we can interpret a character string as an integer expressed in a suitable radix notation. Thus, we might interpret the identifier pt into as a pair of decimal integer 112 and 116 because in the ASCII code, p equals 112 and t equals 116. And if we want to use a single number to represent a character PC, basically we can express them as a radix 128 integer because ASCII code only contains 128 characters, which is 2 to the power of 7. So you can have 112 times 128 plus 106 equals to 14452. So this number can be used to represent PT. So in the context of a given application, we can usually devise some such method for interpreting each key as a possibly large natural number, in which follows we assume that the keys are natural numbers. So using this sense, basically we can express any character strings into representable by the ASCII code as an integer, maybe a large integer. So the first way to find a hash function is to use the division method. The division method is very simple. Basically, it's simple to create the hash functions. Basically, we just simply map a key k into one of the m slots by taking the remainder of k divided by m. That is, the hash function is hk equals k mod m. So, for example, if the hash table has a size m equals to 12 and the key is 100, then basically the hash of k will become 100 mod 12 and it will be the 4. Since it requires only a single division operations, the hashing by division is reasonably fast. However, there are some things that we need to be aware of. When using the division method, we usually avoid certain values of m. For example, m should not be a power of 2, since if m equals 2 to the power of p, then hk is just at the p lowest order bits of k. Unless we know that all lower power order p bits patterns are equally likely, we are better off designing a hash function to depend on all the bits of the key, not just the lower p bits. A prime not too close to an exact power of 2 is often a good choice for M. For example, suppose we wish to allocate a hash table with collisions resolved by chaining to hold roughly n equals 2000 character strings, where a character has 8 bits. We don't mind examining an average of 3 elements in an unsuccessful search. And so we allocate a hash table of size like m equals to 701. We could choose m equals to 701 because it is a prime near 2000 over 3, but not near any power of 2. Treating each key k as an integer, our hash function would be like hk equals k mod 2, mod 701, sorry, not mod 2. So the second method to find a hash function is the multiplication method. The multiplication method for creating hash functions operates in 2 steps. The first step, we multiply the key k by a constant a, which is between 0 and 1, and then extract the fractional term of Ka. So basically you have a Ka mod 1, and Ka mod 1 is actually the Ka, which because you times a fraction number, basically it will not be a integer. So if you find the minus the flow, then basically that will leave you the fraction part of Ka. And then, so Ka will be also within the range of 0 and 1. Now you may be 0, you may be equal here. And then you multiply Ka mod 1. Sorry, this is not, where are we? So this is not Ka, this is Ka mod 1. Okay, sorry. So basically the K mod 1 will between 0 and 1, and then if you multiply with m, then you will have hk from 0 to m minus 1. So if you times k mod 1 with m and then choose the flow, then basically you will get your hash function from 0 to m minus 1. An advantage of the multiplication method is that the value of m is not critical, unlike the division method. We typically choose it to be a power of 2. Suppose that m equals to 2 to the power of p for some integer p, since we can then easily implement the function on most computers as follows. Suppose that the word size of the machine is W bit, and that the K fits into a single word. We restrict A to be a fraction of the form S over 2 to the power of 2 to the S over 2 to the power of W, where S is an integer in the range of 0 to 2 to the w. So basically, we suppose that s is from 0 to 2 to the power of w, and a is in the form of s over 2 to the w. So we first multiply k by the w-bit integer s equals a to the 2 to the power of w, and the result is a 2w bit values r1 times, it would be like r1 times 2 to the w plus r0, where r1 is a high order word of the product and r0 is a lower order word of the product. The desired p-bit hash value consists of the p most significant bit in the r0. So here, this part is the hash function. Although this method works with any value of a constant a, it works better with some values than the others. The optimum choice depends on the characteristics of the data being hashed. And Nuss suggests that a equals to root 5 minus 1 over 2 is likely to work reasonably well. So they suggest that this a can work quite well in most of the cases. So this slide shows an example of the multiplication method. So as an example, suppose we have k equals to 1, 2, 3, 4, 5, 6, and p equals 14. So m equals 2 to the power of 14 equals 16384. And as suggested, we use a equals root 5 minus 1 over 2. So hk should be the flow of m times k times a mod 1. So 1, 2, 3, 4, 5, 6 times a mod 1 is close to 0.041089, and then times 16384, and it's 67.321, and then we choose flow, it will be the 76. So HK will be 76 in this example. So for those students also participate in the computer organization and architectural classes, you may learn that the multiplication and the division takes many more class cycles to be finished than the simple subtraction or addition, and it is worse for the floating-point applications. So it could be like 40 times or 100 times more for a single instruction. But in the algorithm, basically, as long as it is a constant, no matter it's 100, 1000, or 1, as long as it's a constant, it's theta 1. Okay? So no matter how large the constant it is, as long as it is a constant, then it's theta 1. And the other thing is that this is also an example that the computer software engineer and the hardware engineer divides. So an algorithm that is theoretically good performance doesn't guarantee it can be implemented into a hardware algorithm with the same efficiency. Okay? So remember, a multiplication and addition actually has different complexity in hardware, even though in instruction count there are only one instructions. Okay, that's outside the class, but that's what I would want to share as well. If a malicious adversary chooses the keys to be hashed by some fixed hash function, then the adversary can choose n keys that all hash to the same slot, yielding an average retrieval time of theta n. Any fixed hash function is vulnerable to such terrible worst-case behavior. The only effective way to improve the situation is to choose the hash function randomly in a way that is independent of the keys that are actually going to be stored. This approach, called a universal hashing, can yield probably good performance on average, no matter which keys the adversary chooses. In the universal hashing, at the beginning of execution, we select the hash function at random from a carefully designed class of functions. As in the case of quicksort, randomization guarantees that no single input will always evoke worst-case behavior. Because we randomly select the hash function, the algorithm can behave differently on each execution, even for the same input, guaranteeing good average case performance for any input. Returning to the example of a compiler symbol table, we find that the programmer's choice of identifiers cannot now cause consistently poor hashing performance. Poor performance occurs only when the compiler chooses a random hash function that causes the set of identifiers to hash poorly, but the probability of this situation occurs is small and is the same for any set of identifiers of the same size. Okay, let H be a finite collection of hashing functions that maps a given universe U of keys into the range of 0 to n minus 1. Such a collection is said to be universal if each pair of distinct keys K and L belongs to U, the number of hash functions H belongs to H for which Hk equals Hl is at most H over n. In other words, with a hash function randomly chosen from H, the chance of a collision between distinct keys K and L is no more than the chance 1 over n for a collision if Hk and Hl were randomly and independently chosen from the set 0 from the set 0 to minus 1. So here's theorem 11.3. Suppose that a hash function H is chosen randomly from a universal collection of hash functions and has been used to hash n keys into a table T of size m, using chaining to resolve collisions. If key K is not in the table, then the expected length En K of the list that key K hashes to it to is at least most alpha equals to n over m. If key K is in the table, then the expected length E n hk of the list containing key K is at most 1 plus alpha. So we know that the expectations here are over the choice of hash function and do not depend on any assumptions about the distribution of the keys. For each pair K and L of distinct keys, define the indicator random variable xkl equals I, hk equals hl, since by the definition of a universal collection of hash functions, a single pair of keys collides with probability at most 1 over m. We have probability hk equals hl is smaller than equals to 1 over m, so the expectation of xkl is smaller than equals to 1 over m. Next, we define that for each key k, the random variable yk that equals the number of keys other than k that hash to the same set as k, so that we have yk equals sigma L belongs to T and L not equal K, xkl. Thus we have EYK equals E sigma L belongs to TL not equals to KXKL equals to, we move in the expectation, and as we know that this one is smaller than 1 over m, so it's smaller than equals to 1 over the sigma of 1 over m. The remainder of this proof depends on whether key K is in table T. If K not belongs to T, then NH equals Y, and for the L belongs to TL, not K equals to N. So basically, this one is less than N over M is alpha. And if A belongs to T, then because key K appears in list of THK and the count XK does not include key K, we have NH equals YK plus 1. So we have the result NH equals YK plus 1. Thus, ENH equals to EY plus 1 is smaller than equals to n minus 1 over n plus 1, so it's smaller than 1 plus alpha. So, using universal hashing and collision resolution by chaining in an initially empty table with m slots, it takes expected time theta s to handle any sequence of S-insert, search, and delete operations containing n equals big O M insert operations. Since the number of insertion is big O M, we have n equals big O M, and so alpha equals to big O1. The insert and delete operation takes constant time, and then according to theorem 11.3, the expected time for each search operation is big O1. By linearity of expectation, therefore, the expected time for the entire sequence operation is big O(n). So designing a universal class of hash functions may need a little help from the chapter 31, which we haven't covered yet, and maybe will not cover in this class. So let's just assume that we have the knowledge that about the number theory in chapter 31. Okay, so we begin by choosing a prime number p large enough so that every possible key k is in the range of 0 to p minus 1 inclusively. And let the Zp denote the set of 0, 1 to p minus 1, and let Zp star denote the set 1, 2 to p minus 1. Since p is prime, we can solve equations modulo p with a method given in chapter 31 because we assume that the size of the universe of keys is greater than the number of slots in the hash table. We have p greater than m. Then we can define the hash function HAB for any A from ZP star and any B from ZP using a linear transformation followed by the reduction modulo P and then modulo M. So HABK equals AK plus B modulo P and modulo M. For example, with P equals 17 and M equals to 6, we have H348 equals to 5. The family of all such hash functions is HPM equals HAB and A belongs to ZP star and B belongs to ZP. So each hash function HAB maps ZP to ZM. This class of hash functions has a nice property that the size m of the output range is arbitrary, not necessarily prime, a feature which we shall use in section 11.5. Since we have p minus 1 choices of A and p choices of B, the collection of HPN contains p times p minus 1 hash functions. Finally, we will show theorem 11.5. The class HPM of hash functions defined by previously defined is universal. So consider two distinguished keys K, L from ZP. So K is not equals to L. For a given hash function HAB, we let R equals AK plus B mod P and S equals to AL plus B mod P. And we noted that I is not equals to S. It follows that because R minus is equals to A K minus L mod P. So because P is prime and both A and K minus L are non-zero modulo P, so R will not equals to S. So then we can get that A equals to R minus S times K minus L minus 1 mod P, and B equals to R minus AK mod P, where this term denotes the unique multiplicative inverse modulo P of K minus L. Since there are only P times P minus 1 possible pairs, Rs with R not equal S, there is a 1-to-1 correspondence between pairs AB with A not equals to L. Thus, for any given pair of inputs K and L, if we pick AB uniformly at random from ZP star times ZP, the resulting pair Rs is equally likely to be any pair of distinct values modulo P. It then follows that the probability that distinct keys K and L collides is equally to the probability that R equals to S, when R and S are randomly chosen as distinct values modulo P. For a given value of R, of the P minus 1 possible renaming values of S, the number of value S such that S not equals to R and S equals star R modulo M is at most P over M minus 1. So it's smaller than P plus M minus 1 over M minus 1. So it's P minus 1 over M. So the probability that S collides with R when reduced modulo M is at most P minus 1 over M, which is alpha, which is 1 over M. So HPM is indeed universal. Okay, and that ends today's talk.